Hello everyone, welcome to my videos on elementary differential equations. This is video 8 for chapter 5, and the topic for the chapter is the Laplace transform. In this video, we will look at more examples of solving initial value problem using Laplace transform. So here is an example where you have complex roots as the solution for the characteristic equation. Okay, so the equation is the following: y double prime minus 2y prime plus 10y equal e to the negative t. And initial conditions are y0 is 0, y prime 0 is 1. Okay, so before we apply Laplace transform, let's use the method of undertermed coefficients, the one we learned earlier, to find out which terms will be in the solution so we can make a comparison. Okay, so the characteristic equation, r squared 2 times r 10 equals 0 for the homogeneous equation. And if you try to solve this to find the roots, and then you see that this can be written as r minus 1 square, which will be take a 1 from it, and then what remains is 9, okay, which is 3 square. So you see that you can have two compact roots which are conjugates. So is 1 plus 3i and the other is 1 minus 3i. Okay, and then we can write out the form of the solution, which will consist of the general solution for the homogeneous equation plus a particular solution. And the homogeneous solution here would be based on the roots. So it's complex roots, and therefore is e to the real part times t, so just 1, and then sine and cosine of the imaginary part times t. So we have one term with cosine, one term with sine, and then multiply by arbitrary constant. And then for the particular solution, we see that it will match the form of the right hand side. So it's some constant times e to the negative t. And then if we take the Laplace transform of this solution, and we would get something in the following form. So et cosine 3t Laplace transform is this. You can write out the transform for cosine and then do a shift, change all the s into s minus 1. Okay? And then for the one with sine, you can do a same thing. So here a is 3, and then the s minus 1 replacing s because of the shift. And the last term is the exponential function, then we just get a over s plus 1. Okay, so this would give us some idea on which terms to look for in the partial fraction. Because we're not so comfortable with this calculation yet, therefore we try to get some guideline, and later on we will know, and then we don't need to go through that. We'll know how to break it up into partial fractions. All right, so let's take the Laplace transform. Okay, so let capital Ys to be the Laplace transform of little y of t. And then the transform of the derivative will be s times y minus the initial condition. Put in the initial condition, which is 0, you just get sy. And then the second derivative, that's the formula. Wait a second. Okay, there is a y prime here. So this term is 0 and this term is 1, and we get this expression. Okay, now we can put all these into the equation. So this will be transform of y double prime coming from here. And then here is the transform of y, which is this term. And that's 10 times y transformed. Okay, and the right hand side is the transform of the exponential function, is 1 over s plus 1. And then we see that we can solve for y of s, because that's just an algebraic equation for capital Y. Okay, one can move this term 1 to the right hand side, so which is here. And then the left hand side, one can take out capital Y as a common factor. And then I'll collect the terms as square here, 2s here, and 10 here. So it's just like the characteristic equation, okay? Changing the r into s here. Okay, and then the right hand side can be written into a fraction, so s plus 2 over s plus 1. Okay, and then we can divide both sides by this term and get an expression for y of s is just s plus 2 over s plus 1 and this term. Okay, so before we go into partial fraction, let's manipulate this term and write it in a better way, as the way we have done when we try to solve the characteristic equation. So this term can be written as s minus 1 squared plus 3 squared. Because if we have a denominator like that, and with suitable numerators, the inverse Laplace transform would be an exponential function times sine or cosine, okay? Because that we know. So okay, so keep that in mind, and now we want to fit in partial fraction. So we basically have 3 terms. One is for the term s plus 1, so it's a over that. And the other 2 terms will both have this term in the denominator, and then we'll try to fit in the numerator such that the b term here will give us e to the t times cosine 3t as the inverse transform. So then b will be multiplied with s minus 1 on the top. And then the term with the c will be the one that will give us inverse transform. That's e to the t times sine 3t. So therefore I put a 3 here. So this manipulation will just make the inverse transform later much easier. Okay. So now our job is to find these constants a, b, and c such that this fraction will equal to this sum of 3 fractions. Okay, a similar strategy we did is we rewrite this back into a fraction, and then we compare the numerator because the denominators will be the same. Okay, so the numerator on the left hand side is s plus 2, and on the right hand side for the a term will be multiplied by this guy here, and then this guy is multiplied by s plus 1. So that's why I just write everything here and multiply by s plus 1. Okay, so again, using our previous successful strategy, we can choose the value of s such that some constants will be multiplied by 0, so we can solve for the remaining one. So we see that b and c are involved in the term is multiplied by s plus 1. So if we put s to be negative 1, and this term is multiplied by 0, so it's gone. And then we only have a. Then one can easily solve it, right? So negative 1 plus 2 is 1. And if s is negative 1, then I get 2 squared, which is 4, plus 9 is 13. So 13a equals 1, so a is 1 over 13. And then to find the constants b and c, there are actually many different ways of doing this. Let me present a way that I have written down on the notes. So we can compare the coefficient of s squared term. There's no such term on the left hand side, so it's 0. And on the right hand side, what will stand in front of s squared? So here I'll have s squared, which has a in the front. And then here I'll have s times s, which will give me s squared, and it will have b in the front. So I'll have a plus b is 0, which would tell me that b is negative a and is negative 1 over 13. Okay, so now c is the only one that needs to be worked out. Then really there is no trick here. You can set any value of s. Let's say set s to be 0. And then we have 2 here. And then if s is 0 is 1 plus 9, so 10a. If s is 0 here, you get this term is 1, and then this term is -1, so minus b, and plus 3c. Okay, and then a, b's are given, so I have 3c equal to all the rest. Put in the value of a and b. I don't go into the detail. You get that, and then divide both sides by 3, and you find c is 5/13. Okay, so in this way we found constants a, b, and c. So as I said, that is not the only way, and another way would be after you find a, then you can set s to be 1, and then the b term will disappear, and then you will have only a and the c in the equation, where a you already know the value, and then you can find the c right away. Okay, so there are many ways, so let me don't go into too many details there. Okay, so once we have prepared the form of the partial fraction, now taking the inverse Laplace transform is very easy. So we know that the a term gives me the exponential function, and the term b will be the exponential of t times cosine 3t, and the c term will be in front of et times sine 3t. And then we can put in the values of a, b, and c, a and b and c, and we can write out the solution. Okay, and we also see that the terms we predicted using the method of underterm coefficient fits very well here. So exactly we have 3 terms. Okay, so let me take one more example, also in the class of complex roots, and in fact pure imaginary roots. Okay, so we want to solve y double prime plus y equal to cosine 2t, and then y0 is 2, y prime 0 is 1. Okay, so since this is an exploratory example, let's have some guidance. Let's first predict the terms in the solution. So characteristic equation r squared plus 1 equals 0. Then I have 2 roots, pure imaginary plus minus I. That means the homogeneous equation has the general solution c1 cosine t plus c2 sine t. And the particular solution will match the form, so it's a times cosine 2t. There is no sine term because I don't have y prime here. Okay, so in that case, the particular solution is only cosine 2t. There's no sine 2t. You can put in the term b times sine 2t, but that will be 0. Okay, so put it all together, the solution takes this form, homogeneous and particular. Okay, so let's take the Laplace transform, and then we'll see that the transform should take the following form. Some constant, s over s squared plus 1 for the cosine, and for the sine is 1 over s squared plus 1, and then for this cosine will be s over s squared plus 4. Okay, so with that guidance in our mind, now let's solve the equation using Laplace transform. If we take the transform on both sides, so I'll be a bit brief here. So this is the transform of y double prime, gives you s squared y minus 2s minus 1 coming from the initial condition. Okay, and that's y. And the transform of the right hand side, the cosine, will give me s over s squared plus 4. Okay, so we can solve this algebraic equation. We can move the this term here, negative 2s minus 1 to the right hand side and become plus 2s plus 1. And then the left hand side becomes s squared plus 1, s squared 1 times y. Okay, and also we know it's useful to write the right hand side in a fraction. So we'll do that. If we write this in the fraction, we get this. Okay, so this term will be 2s plus 1 times s squared plus 4 over s squared plus 4, and then you join it, and then you open it, and then collect like terms, and this is what one gets. So just a little bit detail I skipped. Okay, now we can divide both sides by s squared plus 1 and get an expression for ys. I'll have this fraction here. And now we need to break this up into partial fraction. Okay, so the rule of the partial fraction is, so these two terms, they are both with the complex roots. So we'll break them up into two separate ones. And then since this is a second order polynomial, this term will actually break up into two terms. We know that one term will give us cosine and the other term will give us sine. So we'll have capital A times S plus B, where A is for the cosine, B will be in front of the sine. Okay, and then the second term is the same, so S squared plus 2 squared, and will also actually be involved in two terms. One is for the cosine, so C times S, and the other term is for the sine, D times 2, because if it were 2, it's sine. So from the previous discussion, we know that this term actually shouldn't be there. So let's see if we actually get D to be 0. Okay, so let's compare the numerators. So this equals that. If I rewrite this into a fraction, the numerator would be the left-hand side, this here, and the numerator here would be this term times this term, which is here, and then plus this term times this term, which I wrote here. Okay, so we have a polynomial of degree 3 on the left and on the right, which will give us 4 constraints in general, right? And we can solve for 4 unknowns. Okay. One way of doing this, well, if we try our previous tricks, we see that if we take any real values of s, and this is never 0, this is never 0, so that trick kind of doesn't really work. So another way of doing this will be expand the right-hand side, write all this out and collect like terms, and then compare the terms s squared, s cubed, s squared, s, and 1, 4 terms. Compare the coefficients, we'll get 4 equations for a, b, c, d, and we can find it. But we can see that that likely would involve quite some work. So what will be the new idea here? And now we see that these terms here will be non-zero for any real values of s, but we can put s to be complex number, pure imaginary number, and with a suitable choice, then this term or this term might become 0. So let's try that idea. Okay, so let's see. Let's set s to be I. Okay, and then remember that I squared is minus 1, and therefore s squared plus 1 is 0. So c and d's are gone. Then we'll only have a and b's. Okay, and then I squared is negative 1, and I cubed is negative I. Let's plug that in. So we'll get negative 2i minus 1 plus 9i plus 4 would equal to ai plus b, negative 1 plus 4, this is 3. Okay, and let's simplify. Find out the real part and imaginary part on the left and on the right. And then on the left, I get 3 plus 7i. And on the right, I'll get a 3 here, multiply onto it, I'll get 3b plus 3ai. Okay, and then we see that the real part must match, then b is 1, and the imaginary part must match, so a is 7 over 3. Okay, now to find c and d, we can apply similar ideas. Let's say we choose s to be 2i, so this term is 0. Okay, and then we know that s squared will be negative 4, and then s cubed is negative 8i. So we plug that in, and then we plug that in, and then here becomes 18i plus 4. And the right hand side becomes 2ci plus 2d, and then s squared is negative 4, so it's negative 3. Okay, so we can collect the real part and imaginary part, and we see negative 4 and 4 cancel, so the real part is 0. And then this and that add up together is 2i. And then you can distribute to the negative 3, so I get negative 6d and negative 6c times i. Okay, then matching the real and imaginary part, we see that d must be 0. And then 6c is 2, so negative 6c is 2, so c is negative 1 over 3. So pay attention that we predicted the d will be 0, and we found that it is 0 here. Okay, now we can put these numbers back in, and then the Laplace transform of the solution now is this, where we just put in the number a, b, and c, d. Okay, and now we're ready to take the inverse transform. Okay, so because the way we prepared it, the inverse transform is now very easy. So 7 over 3, the a term will be in front of cosine t, and the b term 1 will be in front of sine t, and the term c term here will be caused by the source term. This is the particular solution, so it's just cosine 2t. So we easily solved this equation. Okay, so that's the end of these two examples. So to summarize, we can see that we may conclude that using the method of Laplace transform, we see that it handles the solution of this type of problem, that is constant coefficient, and with the source term of a function exponential, sine, cosine, and polynomial. We see that it handles it very well, and it gives exactly the same solution as our previous method. So it's kind of an alternative way of solving these equations. Okay, so we haven't seen clear advantages of doing that, which will come later. Okay, so that's all I have to say for this video, and next time we will see how to solve higher order equations using Laplace transform. So I hope you enjoyed this one, and I hope you join me next time. I'll see you then.